Okay, can you see the screen? My screen? Someone?
Yes, sir. Yes,
Okay.
sir.
All right, let's start because this is just a 50-minute session. Yeah, so I'll continue from where we stopped in the last class. So we were talking about different properties of nanomaterials, and we were discussing the optical property that day when we're talking about the band gap for semiconductor materials. And for metallic nanomaterials, I already said that the color is not like the bulk. That means gold is not golden, silver is not silver, any other metals, okay? They can have many colors based on the size of the particles. Now, how does that happen, or what exactly happens there? So for metallic nanoparticles, we talk about term which is surface plasmon resonance. If you look at the bottom of the slide, it says metallic nanoparticles color changes in spectra due to surface plasmon resonance. Now, what exactly are these surface plasmons that we talk about? Now, I already mentioned once, I think, that the difference between a metal semiconductor and an insulator. Okay, it's all about the band gap. So insulators have a very big band gap, and that's why it's very difficult to transfer electrons from the top of the valence band to the bottom of the conduction band. For semiconductors, this is possible with some amount of energy being fed in. And for metals, you don't really need because metals have a lot of electrons in the conduction band, because in metals, the conduction band and the valence band, they overlap, right? So there is an overlap area. That means all those electrons which are on the top of the valence band are also the electrons in the bottom of the conduction band, because they are overlapping. Let me just show you this. Let me take a blank slide. All right, let's try it here. Okay, so let's talk about metallic particles now. Okay, the color of metallic particles. So if I draw the band gaps now, say this is for, suppose, insulator. All right, this is the valence band, and this is the conduction band, and the difference is huge. Okay, so suppose we are talking about maybe 10 electron volt. Okay, so normally it's difficult to give this much amount of energy. Okay, so this is, suppose, your insulator. Later. All right, now let's draw another one now. Okay, so the semiconductor, now this will be slightly smaller. Okay, the same situation. Now we will say, suppose this is maybe 1 electron volt. All right, 1 electron volt to, suppose, about 5-6 electron volts. Okay, let's say 5 electron volt. So in this range, I mean, this amount of energy is possible to be given to the electrons sitting here to jump over to the conduction band. Okay, and what happens in metals is something like this. Say suppose this is the top of the valence band. Okay, so this is, suppose, the valence band. Okay, now what happens, the conduction band bottom, it's not at a high energy. In fact, it is at a slightly lower energy than the top of the valence band. That means the conduction band bottom is somewhere here. Okay, so this is the conduction band bottom. Okay, so we have a sort of a overlap area here, and most of the electrons are there. And that's why in metals, electrons are freely available for movement. Okay, and that's why they conduct electricity very easily. Okay, so now what happens if you look at a metal now, coming to the color of your metallic nanoparticles. So like I said, there will be a lot of electrons here, lot of electrons, and there is a natural tendency for the free electrons to move to the surface. Okay, so most of the free electrons are available at the surface. You know that, right? Because see, if I have a wire like this, suppose this is my wire. Okay, this is my, I'll draw it slightly bigger. Suppose this is my wire. Okay, and through it I am passing current. That means I am applying a voltage, suppose between these 2 points somewhere, and we have a current flowing, right? Now this current basically is the flow of electrons. Correct? Current flowing this way means electrons are moving this way, right? The electrons are moving this way. So what happens is that the electrons actually, like I said, no, the free electrons have a natural tendency to move to the surface. So even though we have a solid big rod like this for as a conductor, the electrons are actually moving on the surface of the rod. All right, not in the center. That means if I have to draw the cross section, suppose this is the cross section of your wire, right, then most of the electrons will be moving through this part, right, and not the center part. Okay, because of the natural tendency to go towards the surface. So now you know that electrons, they are not static. They are not static. That means they have a natural tendency to be in motion. Right? They have a natural tendency to be in motion. That means they're constantly moving, and at the same time the energy that they have is also varying. All right, it's also varying. That's why we say that typically an electron will have a natural frequency of oscillation. Okay, and when I think that I'm talking about the energy now, so that means for the electron also with time the energy will keep on fluctuating. It goes to a maximum, then again comes down. All right, again comes down, again goes to a maximum, comes down. Okay, this goes on. All right, so with some frequency, suppose f, I'll say n, that means the natural frequency of the electron. Okay, and this happens on all metals. Now what happens when light falls in? See, when we are now talking about the color of the metallic nanoparticles. Now to see something, you have to excite it with light, right? You don't see anything in a dark room, do you? If you close everything, all the screens, close the light and switch off the light, you won't see anything because there's no light coming in that can strike the objects and go back to your eyes, and then you see. Okay, that's why without light you won't see. The same thing here for the metallic nanoparticles also. The color you'll see only when there is light, not in a dark room. That means light has to fall on your metallic nanoparticle surface, right? So if suppose this is a light coming in with a certain frequency, suppose let me call it, normally we say h nu. Okay, so nu is the frequency. Okay, so h is Planck's constant. This is the energy of the incoming light. What happens, this also has a frequency nu, right? This has a frequency fn, that means the natural frequency of the electrons, and light also has its own frequency of oscillation. Now when this falls here, there will be what we call as interference. Okay, that means there will be an effect of these. All right, that means the incoming light will interfere with the oscillations of the electron. Okay, So there will be an interference. So if there is an interference, then, say, let me give you a small example here. Suppose I have a signal which is oscillating in energy like this, all right? Then it comes across another signal with maybe a different frequency, all right? And the result may be that the combined effect might give it a much higher intensity, all right? Or if it, so this is called positive interference, all right? This is positive. That means it increases the intensity, and it might be the other way. It might even reduce the intensity, make it very, very small, okay, because of, the interference effect. So this is called negative interference, right? And then for a certain frequency, this positive interference that I'm showing here will go to a maximum peak. For a particular frequency of the incoming signal, this might even go even higher to the maximum possible, okay? And that situation is called as resonance, okay? That means when light falls, and then there's also natural oscillation of the electrons happening, and then though both of these signals, they interfere with each other, and at a certain frequency this will go extremely high, okay? So at that particular frequency that goes extremely high, we call as resonance. Then what will happen? There will be radiation, okay? Now this movement of the electrons, we actually call them as plasmons, okay? And this is happening at the surface. M-O-N, very difficult to write with a stylus, but anyway. So, and this is happening at the surface of the metallic nanoparticles, and that's why we call it as surface plasmon. All right, and then light falls on it, and there is a resonance at a particular frequency, and then we result in what we call as surface plasmon resonance. Okay, and that particular frequency, the nanoparticles radiate out the energy. That means I'll draw the nanoparticle somewhere below. Okay, this is our nanoparticle, and then it has its own, the electrons on the surface has their own natural frequency. Light is coming into a certain amount of frequency, all right, there will be resonance, and then this will radiate out that frequency which has resonance, all right? So now we're talking about visible light. So if the frequency at which the resonance happen is red, then you are going to see red, right? If it is at blue, you are going to see blue, all right? That's how it happens, all right? And this resonant frequency depends upon the size of the nanoparticle, mainly because the size decides the number of electrons that is available on the surface. Okay, smaller the size, the relative number of electrons is more as compared to larger the size. Relative, that means the total number of electrons, the fraction that will be on the surface will be more when the particle is small. Okay, and when it goes small, normally the frequency goes high and you see more towards blue color, okay, and in the other case it's more towards red color. Okay, so that is the concept of surface plasmon resonance, and that is the why we see all these different colors in metallic nanoparticles. Okay, all right, let's continue to the slide. All right, so we already talked about optical properties. Moving on to electrical property. So the electrical conductivity decreases with a reduced dimension, okay, due to increased surface scattering. Right? Now, What it means, it is saying is a reduced dimension means the particles, if you're taking it smaller and smaller, the electrical conductivity also decreases. Now again, if you think about it, the electrical conductivity happens because of electrons present on the surface. And these are free electrons in the sense that they're not strongly bonded to the central nucleus. Okay, so you don't need enough energy to make them move. That means a small amount of voltage applied, that means a bias, small amount of potential difference will make these electrons move. All right, that means we put a small voltage, automatically you'll see current because of the electrons moving. But when the particles become smaller and smaller, then what happens is there is increased surface scattering. Now what is scattering? See, as the electrons move, they come across certain obstacles in the form of other atoms, right? So there's the material is filled with atoms. So atoms means there's a nucleus with protons and neutrons, right? And of course there will be electrons also moving around. So those free electrons, as they move through this maze of protons, neutrons, and other electrons, they strike. Okay, they do not always find a free pathway. They hit other electrons. They sometimes at a higher acceleration. They sometimes go very near to the protons because the protons anyway try to pull them because they have positive charge. Electrons have negative charge. So there are a lot of obstacles, and that's why these obstacles scatter. Scatter means it changes its direction. Okay, they move here and there. Okay, and that is the reason why if the particle goes smaller and smaller, the density, or the atoms are much more closer, and there's so many atoms on the surface, and the electrons have to be at the surface for conductivity, and that's precisely they will have more scattering, and that's why the conductivity will go down. Okay. Now, electrical conductivity increases due to the better ordering and ballistic transport. Now, these are two different situations, so ultimately the result is a combination of these two. So for one reason, because of scattering, the electrical conductivity decreases, but because of the better ordering, means the arrangement of the atoms. All right, the atoms, as it goes smaller and smaller, you find that the atoms are more precisely placed in the right positions. All right, that means they do not really have too much of defects in the crystals. The atoms are in the right places, and that's why when you apply a bias or there's a potential difference, the electrons tend to, move through what we call as ballistic transport. Okay. Now, this concept increases with decrease in size. All right. So ultimately, we have a mixture of these two. That means, and for certain reasons, the conductivity decreases, and there are a few other reasons for which the conductivity increases. Okay. So that's about the electrical property. Talking about the magnetic properties, ferromagnetism disappears. Now, ferromagnetism, basically, you know what is magnetism, all right? So, so a magnet, if I say a magnetic material, then I mean that it is already a natural magnet, all right? It has a strong magnetic field present around it and through its body, okay? So a typical magnet that we talk about, okay? Earth itself is a magnet. Now, that's a permanent magnet, all right? So when you say magnet, we actually refer to a permanent magnet. Now, ferromagnetism, I'm sure you studied all these in physics in class 12 or even 10 maybe. So you know, like iron or something, if you place close to a magnet, they also start getting magnetized. All right, that means the atoms there, the electrical orientations, the spin in the electrons, they align themselves with the magnet, and they also start becoming like a magnet. All right. So ferromagnetism is like a temporary magnetism, but you keep on you know keeping a say iron for many days or months to with near a magnet, it might make it or convert it to a permanent magnet finally. But ferromagnetism basically relates to that. As long as the energy is there, the magnetic field is there to orient the electrons, then it is a ferromagnetic. So typical iron is a ferromagnetic material, copper is a ferromagnetic material. Okay. Now these materials, even iron, if you make it into smaller and smaller and smaller into a nanomaterial, then it will move away from ferromagnetism. Okay. So it will not really exhibit the property of ferromagnetism, and it will move towards what we call as paramagnetism. And in fact, the correct term at the nanoscale is super paramagnetism. Okay. And this is precisely because of the huge energy that is there. Okay. So paramagnetism, super paramagnetism concept is more like, see, say ferromagnetism basically talks about orientation of the electrons in the same direction of the magnetic field that is interacting with it. Paramagnetism happens the other way, opposite to it. All right. So the field that is exciting, the magnetic field, the one that is generated in the material will be in the opposite direction. And in superparamagnetism, it's very difficult to predict. Okay, it can switch over. That means at one moment it is in one direction, instantly after some time it might be in the other direction. Okay, so the magnetic moment is very difficult to predict in nanomaterials, and that's a stage we call as super paramagnetism. All right. Then another property is self-purification. That's why nanomaterials are considered to be very, very pure. Okay, because they automatically, as they form, they, through a natural tendency, they try to purify themselves. That means purify in the sense that if there are certain defects in the form of maybe excess atoms or lack of atoms in the right places, right? We call them as voids or vacancies. So as a material is building up, it's not necessary, or you cannot actually say that all the atoms will go to the right places. They may not. Sometimes atoms just sit here and there in between the allotted spaces. Now those are defects, right? So in a nanomaterial, there is a natural tendency, because the surface is so large as compared to the total volume, there is a natural tendency for these to move towards the surface. And once they reach the surface, there's every possibility they get removed from the system, right? So defects are at the surface, and when they're at the surface, because the surface is highly reactive, you understand a defect means like a vacancy. That means there is no atom. So this big vacancy will move, in a sense that atoms from the surface will move in, and it will appear as the vacancy is moving out. Okay, and once it reaches the surface, it has always another possibility to pull in another atom and complete the remove the vacancy. All right, removing the vacancy means removing the defect. All right, so that's the process goes, and that's why mostly, all these impurities, they get removed. Now dislocation is something that is more like your something like what I can say, or the tectonic belts. Suppose your tectonic plates, about all these earthquakes happening, right? Because of the tectonic plates under the surface of the earth, and these tectonic plates actually move. Now, when a crystal is formed, then all these arrangement of atoms, like I said, arrangement of atoms in a particular pattern, they may be different sections in your nanoparticle. In one part the pattern is one, in another part of the particle the pattern may be slightly different. Okay, so that may also happen. It is not necessary the complete nanomaterial or complete particle will have the same orientation. All right, so then those separations between these different types of orientations are what we call as dislocations. Okay, then these can actually move from here and there, so it's more like the tectonic plates. Okay, so all these will vanish or get minimized if we make the particles smaller and smaller and smaller, right? So ballistic transport, as I just mentioned, is the transport of electrons in a medium having negligible resistivity. That's why we call it ballistic. Okay, it means moves very fast, there's no obstruction. Okay, so the scattering thing is minimized. So if there is no scattering, then the electrons simply obey Newton's second law of motion. You know Newton's second law of motion, what was it? It says that the mathematical expression is force is equal to mass into acceleration. Okay, so it says, the acceleration of a material with certain amount of mass depends upon the force at which the force that impacts the material with certain amount of mass m, and then the acceleration a results. Okay, so at the atomic and molecular level, quantum mechanics is, you know comes in. Okay, quantum mechanics, I'm always talking about quantum mechanics, means quantum means in packets. All right, it's not continuous. So anything as you go down smaller and smaller are not continuous but rather discrete, right? So we have discrete system, and if we talk about the energy levels, I don't know if you know energy levels. You can stop me anytime you have any doubts. I think I have pictures to show you later, but look at the thing now. As we were talking about valence band, conduction band in a system, right? So suppose I have a bulk material, all right, a semiconductor bulk material. Okay, now like I said, mostly there's a tendency for the electrons to be at the top of the valence band, and then if we provide sufficient amount of energy, it jumps up to the conduction band. Okay, and this gap in between, okay, is called the forbidden band. That means an electron, if it somehow jumps to that part which is in between, it cannot stay there. There is no possibility of the electrons to retain that energy for some time. They automatically fall back to the valence band. Okay, so these are not allowed region of energy. Fine, they can remain in a particular level for some time only in the conduction band. Okay, that means that much of energy they have to gather to, once they move into the conduction band, they can stay there for some time. Okay, it's called a quasi-stable state. Quasi means temporary. Okay, quasi-stable state. Now in a bulk material, this conduction band, the moment it starts, it's continuous after that. Any energy, okay, you pull in, the electron will go and stay there for some time. But as you go smaller and smaller in the size, then what happens? This gets discretized. That means it's not continuous. That means even if the electron jumps over to the conduction band, it cannot have any type of energy. I mean, whatever energy it goes in, it cannot stay there. It has to somehow move to some allowed energy levels, not continuous, which are discrete. You understand? That means I'm just giving a very odd example. Say, suppose the bottom of the conduction band is at, suppose, 2 electron holes, right? Now in a bulk material, any electron moving over to 2.1, 2.11, 2.15, 2.22, 2.23, whatever, they will get a state to stay there for some time. But in a nanomaterial, when it gets discretized, then maybe the electron can only stay at 2.1 or 2.2 or 2.3. Okay, that means if it goes to 2.32, it will lose that 0.02 energy, then come to 2.3, and then only it can stay. You understand? So these are discrete levels. I have a picture I'll show you later. Okay, so at the everyday scale, Newton's laws work fine. That is the classical physics. Newton's 3 laws work very nicely at the bulk, but when you go down, it does not fall. The classical physics does not work, and we go for quantum physics. So nanomaterials are in a borderline region where either or both approaches may be appropriate. Okay, so it's a bit tricky. All right, that means both of them may come into play, the classical mechanics as well as the quantum mechanics. But you go smaller and smaller in size, the classical mechanics fades away, and it goes purely into quantum mechanics. Strong nuclear force. All right, so the nuclear force is very, very big. It's huge. So they hold the nuclei together. Nuclear force means the interaction between the nucleus. Act only at nuclear distances. That's a typically of around 10 to the power of -5 nanometers at this distance. So atoms are very, very closely packed. Okay, And weak nuclear forces also tend to come in. All right. Now, this is like nuclear beta decay is very difficult to explain for you at the moment, but you can actually go through. But I'll send you a small note also on what exactly I mean here. Okay. But the thing is, what I'm trying to say is that there may be strong nuclear forces happening, and there may be very weak nuclear forces also acting. All right, and the combined effect is prominent. So, electric and magnetic properties are dominant at the atomic and nanotech scales. They're very, very dominant. Gravitational is the other way, dominant at everyday world scale. That means at the macro scale, gravitation is dominant. Gravitation means the effect of gravity, you know. The art I told you is like a magnet and it pulls everything towards its center, right? So, but if you go to the nanoscale, it becomes so small that gravity cannot have an effect on it, all right? So, the gravitational force is given by what? mgh, right? The mass is a big factor there, and for nanometers the mass is so small that the gravitational effect becomes negligible. All right, now talking about diffusion, you know this diffusion is a movement of atoms or molecules from higher concentration to lower concentration. Okay? That is a typical definition of diffusion. So what happens at the nanoscale? Let's see. So small particles, so normally if you talk about molecules suspended in some liquid or dust particles in the air, okay, they move randomly in zigzag paths. We know that the term is called Brownian motion. You cannot predict the movement. It can go any way it want to. I mean, it just happens, and this happens because of the lot of collisions happening between themselves, okay? So particles spread out when introduced into a medium at one point. It's spread out in the sense they move from high concentration to lower concentration. So the typical example is a perfume in a room. You spray the perfume in one corner of the room, stand at the other corner of the room. Within a few seconds, maybe you will smell it. Okay, that means it has moved. Obviously, where you spray, at that part it has the maximum concentration, and the other parts it was zero concentration initially, and then this diffusion starts, and after some time it is even all over, right? The kinetic energy, because of these movements, that's actually directly related to the temperature. Okay, because higher the temperature, more will be the kinetic energy because the velocity increases. Average particle speeds decrease as mass increases, right? So more massive particles diffuse more slowly. It is very obvious, you know this, right? That if you're doing a marathon or you're running, the fat guys move much slower as compared to the thin ones, right? So the mass plays a big role in the velocity or the speed at which a particle moves, right? So that's why bigger particles that will move very, very slowly. So if your perfume has very, very big molecules, then those type of perfumes will take more time than those perfumes which have smaller molecules, okay, because smaller molecules will move faster. Now there is a change in the melting point also. So the melting point at the bulk scale and the melting point at the nanoscale are different for the same material, okay. So what is a melting point if you have to define it? So temperature at which the atoms, ions, molecules in a substance have enough energy to overcome the intermolecular forces that hold them in a fixed position in a solid. That's why. So they, as you give more and more energy in the form of heat, because to melt something you have to heat it up, right? So you give it more and more energy, then the electrons together with the atoms, basically they are, because of a lot of vibrations in the lattice, there will be a lot of vibrations because of the excess amount of energy coming in, and these vibrations tend to force them away from each other, and that's why it goes to a stage when the distance is such that it is no longer a solid, right? If the distance or separation between the atoms gives to a certain distance, then we say that it must move from the solid to the liquid level, okay. So this is change in phase, right? So surface atoms require less energy to move because they are in contact with fewer atoms of the substance, right? So what we call as dangling bonds, some bonds are free because there's nothing above, there's nothing outside. So surface atoms, they are not very strongly bonded. All right, there's an example. You see the atom inside, it is in touch with many more. This particular is in touch with 7 atoms, whereas those at the surface, they are having, they are in contact with 3 atoms. That obviously they are more easily breaking the bonds and moving aside. Okay, so that's why if you melt something, you'll observe that melts at the surface, right? You take an ice cube and put it somewhere, you'll gradually see it's melting from the surface. It's not directly melting out from inside, okay? Because the surface atoms are loosely bonded. So if you look at this plot here now, right? So as the particle size goes smaller and smaller and smaller, the melting point also drops. Okay, and if you look here from around 5 nanometer or 6 nanometer, the drop is very, very sharp, right? So typically above, it's almost flat, gradual decrease, but here after about 5 nanometer, it's sharply decreased. That means below 5 nanometer, there is a huge decrease in the melting point of a material, right? That means a typical material, suppose it melts at 1000 degrees at the bulk scale, and the nanometer or 5 nanometer, less than 5 nanometer size, it might even melt at 200 degrees centigrade. Okay, so that's the difference, but the material is the same. Okay, there's no difference in the material, it's the same, only the size is small. Okay, so the total surface area or the number of surface atom increases, reducing size of the particles. And you see the difference in the melting point can be as high as 1000 degrees, like I told you, no? If something melts at 1000, the next time it melts at 100 degrees, then there's almost 900 degrees centigrade difference, right? So this basically shows the surface atoms, okay, with particle size. Okay, so you see the particle size goes down, so surface atoms goes on increasing very sharply. After 5, now normally this 5 is a very key number. After 5, you see it just abruptly jumps up. That means the percentage of atoms, on the surface is much higher here, and in the bulk it's much lower. Okay, so the bulk atoms gradually with increase in size, they increase, and the surface atoms decrease with increase in size. Okay, so this table basically compares the macro scale with the nanoscale. Okay, so the majority of the atoms in the macro scale are inside the material. All right, majority is inside. I have 5 minutes for this class, but that's okay. We will again continue tomorrow with this same topic, but let's continue till this class finishes off. So I see about 16 participants, huh? That means 15 of you and myself. But I don't want to see 30 attendance coming in after the class, okay? All right. Anyway, okay, so you see, this is the situation here. The number of surface atoms is much more as compared to here. Okay, so if you change an object size at the macro scale, it has a very small effect on the percentage of atoms on the surface. Okay, that means even if you make it smaller or bigger at the macro scale, hardly makes a difference, but at the nanoscale it makes a huge lot of difference. The next particle, if I make it even smaller, then all the surface atoms will be, fraction of surface atom will be even more, right? So it has a big effect on the percentage of atoms on the surface. And the melting point does not depend on the size at the macro scale, right? That means a block of say a sphere of 10 centimeter diameter and a sphere of 1 meter diameter or 10-meter diameter will have the same melting point, right? But if you go to the nanoscale, it will go down. Okay, the same material will have much lesser melting points. Now talking about the lattice constant I mentioned before once that it is the space between the atoms, right? The spacing between the atoms. and they are not always same in all the directions. Okay, that means if I say x, y, and z dimension, then in particular crystals, the atoms in the x direction, the spacing is different with the atoms in the y direction and the atoms in the z direction. Okay, so it all depends upon what type of crystal we're talking about. But anyway, all these parameters, then we'll have three parameters, a, b, and c. All right, so each will have different values of lattice constant. Fine. So it says the surface atoms and molecules have fewer nearest neighbors. Already we mentioned, right? That means a few of the bonds are free because there is nothing on one more side, right? And that is what we call as dangling bonds. See here, these are given here like this round. So these are basically dangling bonds. That means all these free bonds, they basically bond to itself, right? The atom itself, they're bonded to the atom itself, but they can quickly go and have a bonding with some foreign atoms coming in. All right, that's why we say the surface is very, very reactive. It happens for all surfaces, even at the macro level. But since at the nano level, the surface is much more, that's why nanomaterials are much more reactive. Okay, so we call them as dangling or unsatisfied bonds. So that's why, an inwardly directed force, bond distance between the surface atoms or molecules and the subsurface atoms or molecules is smaller than that between interior atoms or molecules. Okay, that means if these are the surface, so there's some pressure going on, then these gaps will decrease. All right, so interatomic spacing will decrease. All right, it's more like some form of elastic thing happening that we forcefully make them smaller, and the moment we go make them smaller, the spacings will be less. Okay, are we still there or we are finished? No, we are still there. Okay, good. So for very small particles, decrease in bond length between the surface atoms and the interior atom becomes significant. Okay, and the lattice constant of the entire solid particles reduce. So the lattice constant means the spacing between the atoms in various directions, so they tend to decrease. Okay, we finished. Okay, then we'll continue tomorrow from the next slide. Fine.
Hello, sir.
Yeah, yeah, tell me. So we'll stop today.